Welcome to the session on properties of Laplace transform. In the previous session, we discussed the Laplace transform of some elementary functions. Here, we shall discuss some properties of Laplace transform. The Laplace transform of a function f of t is defined as L of f of t equal to, which is a function of s. The definition is integral from 0 to infinity e raised to minus st into f of t dt, where s is a complex variable parameter. That is, in order to find the Laplace transform of a function, we just multiply the function with e raised to minus st and then integrate between the limits 0 and infinity. The first property is the linearity property. That is, if c1 and c2 are two constants and f1 of t and f2 of t are two functions of t, then Laplace transform of c1 into f1 of t plus or minus c2 into f2 of t is equal to c1 into Laplace transform of f1 of t plus or minus c2 into Laplace transform of f2 of t. We have to prove this property. By definition, L of c1 f1 plus c2 f2 is equal to integral from 0 to infinity c1 f1 plus c2 f2 into e raised to minus st dt. That is equal to, we can open this this bracket, and we can split this single integral into two integrals. That is integral from 0 to infinity c1 f1 e raised to minus st dt plus integral from 0 to infinity c2 f2 e raised to minus st dt. That is, the c1 can be taken outside. Then integral from 0 to infinity f1 of t into e raised to minus st dt is Laplace transform of f1 plus this is c2 into Laplace transform of f2. Similarly, we can prove L of c1 f1 minus c2 f2 is equal to c1 into L of f1 of t minus c2 into L of f2 of t. We can generalize this property for n functions. That is, Laplace transform of c1 into f1 plus or minus c2 into f2 plus or minus c3 into f3 plus or minus etc. plus or minus cn into fn, where c1, c2 etc. cn are n constants and f1, f2 etc. fn are n functions of t. Consider the example. Consider the function f of t equal to sin 3t into sin 2t. We can write this function sin 3t into sin 2t as 1 by 2 into cos 2t minus cos 5t, because minus 2 sin a cos b is equal to cos a plus b minus cos a minus b. Okay. Therefore, Laplace transform of this function sin 3t into sin 2t can be written as Laplace transform of 1 by 2 into cos 2t minus cos 5t. This 1 by 2 can be taken outside of the Laplace transform, and we can write this term into two terms, that is 1 by 2 into Laplace transform of cos 2t minus Laplace transform of cos 5t, which is equal to 1 by 2 into Laplace transform of cos 2t. So we have Laplace transform of cos at is equal to s by s square plus a square. Therefore, here instead of 8 is 2. Therefore, Laplace transform of cos 2t equal to s by s square plus 2 square minus, here instead of a it is 5. Therefore, Laplace transform of cos 5t is equal to s by s square plus 5 square. This is the Laplace transform of this function. We used the linearity property of Laplace transform. Now consider this function f of t equal to sin square t. We have sin square t is equal to 1 minus cos 2t all divided by 2. Therefore, L of sin square t, that is L of f of t, is equal to Laplace transform of 1 minus cos 2t divided by 2, which is equal to 1 by 2 into Laplace transform of 1 minus cos 2t. This is equal to 1 by 2 into Laplace transform of 1 minus Laplace transform of cos 2t. That is 1 by 2 into Laplace transform of k is that k by s, where k is a constant. Therefore, Laplace transform of 1 is 1 by s minus Laplace transform of cos 2t is s by s square plus 2 square. Now, the second property of Laplace transform is the shifting property. It is known as the first shifting property. That is, if f of s is equal to Laplace transform of f of t, then Laplace transform of f of t multiplied by e raised to a t is equal to f of s minus a. This is the first shifting property of Laplace transform. First shifting property. That is, the Laplace transform of a function multiplied by e raised to a t is a function of s minus a. We just replace s in f of s by s minus a. Then we will get the Laplace transform of e raised to a t into f of t, where f of s is the Laplace transform of the function f of t. We can show this property, we can prove this property by the definition of Laplace transform. F of s, L of e raised to a t into f of t is equal to integral from 0 to infinity e raised to minus st into, here the function is e raised to a t into f of t, by the from the definition of Laplace transform we can write like this. This is equal to integral from 0 to infinity e raised to negative of, we can write this as e raised to negative of s minus a into t f of t dt, which is equal to, here this is the definition of Laplace transform. That is, here we used s in the exponent of e minus s into t f of t dt. Comparing with this definition, here s minus a instead of s. On comparison, we can write this as a function of s minus a, f of s minus a. Here it is f of s. Therefore, we can write this integral as a function of s minus a. That is, if we know the Laplace transform of a function f of t, then we can write the Laplace transform of the same function multiplied by e raised to a t as a function of s minus a. That is, it needs only to replace s by s minus a in the original Laplace transform f of s, which is the first shifting property. Therefore, we know we have Laplace transform of k is equal to k by s, means Laplace transform of k into e raised to a t is equal to k by s minus a. Just replace s by s minus a by the shifting property. In particular, L of 1 is equal to 1 by s, and we have L of e raised to a t is equal to 1 by s minus a. We can find this by the definition of Laplace transform. Note that e raised to a t can be written as 1 into e raised to a t. That is, 1 is multiplied by e raised to a t, and the Laplace transform of 1 by s. Then, by the first shifting property, Laplace transform of 1 multiplied by e raised to a t is equal to 1 by s minus a. But L of e raised to a t is 1 by s minus a. We just proved in the previous session. Therefore, by first we just verified the first shifting property for the function 1. It is true. Consider this example. Consider the function f of t as f of t equal to t cube into t cube plus 3 e raised to 2t minus 5 into sin 3t into e raised to minus t. We have to find the Laplace transform of this function. That is, a combination of algebraic function, exponential function, and trigonometric function, and it is multiplied by e raised to minus t. Means we have to find, first of all, we have to find the Laplace transform of this function, this combination, and we can replace s by s plus 1, because here instead of a it is minus 1 in the shifting theorem. Therefore, Laplace transform of t cube plus 3 into e raised to 2t minus 5 sin 3t can be written as, by the linearity property, we can write the Laplace transform of this combination as the corresponding Laplace transforms of the individual terms, and the corresponding constants from each term can be taken outside. Therefore, this is equal to Laplace transform of t cube plus 3 into Laplace transform of e raised to 2t plus, sorry, here minus 5 into Laplace transform of sin 5t, which is equal to, we know that Laplace transform of t raised to n is equal to gamma n plus 1 divided by s raised to n plus 1. If n is an integer, gamma n plus 1 can be written as n factorial. Therefore, this is equal to n factorial divided by s raised to n plus 1. And so, Laplace transform of t cube is 3 factorial divided by s raised to 4. Here n is 3, therefore n plus 1 is 4, plus 3 times Laplace transform of e raised to at is 1 by s minus a. Therefore, Laplace transform of e raised to 2t is 1 by s minus 2 minus 5 into Laplace transform of sin at. These are the elementary functions and corresponding Laplace transforms. A by Laplace transform of sin at is a by a square plus a square. Therefore, here 5 into Laplace transform of sin phi t means here instead of 8 is 5 divided by a square plus phi square, which is equal to 3 factorial is 6 divided by s raised to 4 plus 3 by s minus 2 minus it is 5 into 5 is 25 divided by s square plus 25. This is the Laplace transform of this combination of 3 functions, and therefore, by first shifting property we can replace s by s minus a. The property is Laplace transform of e raised to at into f of t, that is f of t is multiplied by e raised to at, then the corresponding Laplace transform is can be obtained. The corresponding Laplace transform can be obtained by replacing s by s minus a in f of s. Here this is f of s. Instead of a, here it is minus 1. Therefore, we can replace s by s plus 1. Therefore, the corresponding Laplace transform, that is Laplace transform of the given function L of t cube plus 3 e raised to 2t minus 5 sin 3t multiplied by e raised to minus t is equal to 6 divided by s plus 1 raised to 4 plus 3 divided by s plus 1 minus 2 minus 25 divided by s plus 1 the whole square plus 25. We just replaced s by s plus 1. It is 6 by s plus 1 all raised to 4 plus 3 by this is s minus 1 minus 25 divided by this is s square plus 2s plus 1 square plus 25 is 26. Now, another property is the times time change of scale property. That is, if Laplace transform of a function f of t is capital F of s, then the Laplace transform of the function f of a t, which is equal to 1 by a into f of s by a. That is, we changed t as a into t, which is the change of time scale property. If Laplace transform of a function is f of s, then we can obtain the Laplace transform of the corresponding function f of a t by replacing s by s by a and then multiply by 1 by a. If we change t as a into t, this is the change of time scale property. By definition, the Laplace transform of f of a t is equal to integral from 0 to infinity e raised to minus st f of t dt, which is equal to, sorry, here f of, not f of t, f of a t, f of a t dt. A is a constant. We use the substitution a t is equal to some u, so that a into dt is equal to du and dt is equal to 1 by a into du. When t equal to 0, u equal to 0, a into 0 means 0. As t tends to infinity, u also tends to infinity. Therefore, the limits of integration remains the same. This integral can be written as this is equal to integral from 0 to infinity e raised to minus s. A t equal to u implies from here we can write t as u by a, that is e raised to minus s into u by a. F of a t means f of u, dt is 1 by a du, which is equal to integral from 0 to infinity e raised to, we can write this term as e raised to minus s by a into u, f of u du. This 1 by a is a constant, that term can be taken outside of the integral. This is equal to 1 by a into, comparing this with the definition of Laplace transform. This is the definition, that is f of s equal to integral from 0 to infinity raised to minus st f of t dt. Here s, therefore it is f of s. Similarly, instead of s, here it is negative, s by a. Therefore, this is a function of s by a. That means Laplace transform of the changed function f of a t is equal to 1 by a into f of s by a. This is the change of scale property. Consider this example. We have the Laplace transform of sin a t, sorry, sin t, not sin a t, sin t, which is equal to 1 by s square plus 1. Therefore, by the change of scale property, we can write L of sin a t. Instead of t, we used a into t, that is equal to 1 by a into f of s by a. This is the property. Just replace s by a and multiply by 1 by a. Means here this is f of s. For this L of sin a t equal to 1 by a into 1 by, we have to replace s by a square plus 1. That is equal to 1 by a into 1 divided by s square plus 1, which is equal to 1 by a into 1 by s square plus a square divided by a square, that is equal to 1 by a into, consider the reciprocal of this term, that is 1 by a square plus a square by a square means a square divided by a square plus a square. A square divided by a means a by a square plus a square, that is Laplace transform of sin a t equal to a by a square plus a square. Next property is the Laplace transform of derivatives. If Laplace transform of f of t is equal to f of s, then the Laplace transform of fn t, fn means the nth derivative of f of t, which is equal to s raised to n into f of s minus s raised to n minus 1 into f of 0 minus s raised to n minus 2 into f dash of 0 minus etc. minus s raised to 0 means 1 into f of 0. Here it is this is capital F of s, that is the Laplace transform of the function f of t. Here f of 0, f dash of 0, etc. The last term, sorry, the last term is n minus 1th derivative at 0, fn minus 1 at 0. F of 0 means value of f of t when t equal to 0. F dash of 0 means value of f dash of t at t equal to 0, and so on. F n minus 1 0 means value of f n minus 1th derivative at t equal to 0. In order to write this expression, there is a condition. All these derivatives, that is f dash of t, f double dash of t up to n minus 1th derivative of t should be existed. Then this is the Laplace transform of the derivative of f of t. In particular, we can write Laplace transform of f dash of t is equal to s into f of s minus f of 0. Laplace transform of f double dash of t is equal to s square into f of s minus s into f of 0 minus f dash at 0. Laplace transform of the third derivative, which is equal to s cube into capital F of s minus s square into f of 0 minus s into f dash at 0 minus f double dash at 0. That is, if we consider the first derivative, there exist two terms in the corresponding Laplace transform. This is the second derivative of f. In the Laplace transform of f double dash, there is 3 terms, and so on. These are useful in the application of Laplace transform. That is, these are used to this property will be used to solve an initial value problem, which we will discuss later. Now let me conclude this session. In this session, we discussed some properties, namely linearity property, first shifting theorem, and change of time scale property, and transform of derivatives. Thank you for listening this class. Have a nice day.